Hello friends, my name is Chinmay Deshpande. In this video lecture, we are going to discuss about a topic from power system stability. The name of the topic is Introduction to the Power System Stability. Basically, the stability of an interconnected power system is its ability to return to the normal or the stable operation after having been subjected to some form of the disturbances. We know that modern power system is interconnected system consisting of hundreds of generating stations and thousands of load centers interconnected to each other. Modern power system always operates under a complex interconnections, controls and extremely stressed conditions. Whenever the power system operates in the steady state condition, that is whenever there is no any disturbance or the fault, the system is said to be stable. But if a system is perturbed by or disturbed by a certain disturbances, there will be a readjustment of the voltage angles of the synchronous machine. It may result into the problem of stability. This creates unbalance between a system generation and load, which results in establishment of new steady state condition with the adjustment of the voltage angles. The power system is an extremely non-linear and a dynamic system with operating conditions or the parameters which are continuously varying. Hence, stability of the system is the function of initial operating condition and type or the nature of disturbances. The disturbances could be major one such as fault, sudden loss of generator, short circuit of line or a combination of such events. Due to load changes continuously, it also affects input side. The system must be in a position to be able to adjust the changing conditions and operate satisfactorily. The system must be withstand large disturbances which may even cause structural changes due to isolation of some faulted elements. It is impossible to design a system which is stable under all the disturbances. The power system is generally designed to be stable under those disturbances which have high degree of occurrence. Now, the stability of an interconnected power system is its ability to return to the normal or the stable operation after having been subjected to some form of the disturbances. With interconnected system continuously growing in size and extending over vast geographical regions, it is becoming increasingly more difficult to maintain a synchronism between various parts of the power system. The random changes in the load are taking place at all the times with subsequent adjustments of the generation. If the oscillatory response of the power system during the transient period following the disturbance is damped and the system settles in a finite time to a new steady operating condition, then we can say the system is stable. And if the system is not stable, it is considered as system will be unstable. This primitive definition of the stability requires that the system oscillations must be damped. Let us consider this is analogy of, we can say, the stability. So this is the ball with position 1, this is position 2 and this will be a position 3. The stable equilibrium corresponds to when the ball is resting at the bottom of the ball. So here we can say the position 1 is nothing but a stable position. The unstable equilibrium corresponds to when the ball is resting on the edges of this particular structure. So here what we observe, it is possible for the ball to be rest, that is in equilibrium in both the positions. Here this is the second diagram. This will be a stable equilibrium, this will be unstable equilibrium. The stable equilibrium is resilient to the disturbances. Now if we shake the table or if we give the ball a push, what happens? The ball in the stable equilibrium will move but then return to the stable equilibrium. So this is what is the analogy of power system stability. Let's take the second analogy also. Dropping a marble into a pitcher of the water, that is a container of water in which water is stored, it provides a suitable analogy to understand why the operating condition makes a difference in maintaining transient stability. So let's say this is the pitcher which is full of water, and here we can say, here suppose there is one marble which is placed. Now take a pitcher, that is a large jug, and fill it with the water to a quarter its capacity. Now drop a marble into the pitcher. The dropping the marble is related to a disturbance in the power system. In this situation, no water from the pitcher will splash out, come out, indicating that the system will be stable. But if the pitcher with water close to its brim, that is the water is filled up to, we can say, up to this level. This is what is the level, up to the brim, if the water is filled. And now drop the same marble into the pitcher. What happens in this case? The water will splash out, which indicates that system is unstable. So in these two situations, the same disturbance was created. However, the system was operating at a different condition. And in the latter situation, the system was more stressed because water was filled up to the brim of this pitcher. Again, this analogy illustrates that the degree of stability is dependent on initial operating condition. So that's why stability is the condition in which the various synchronous machines of the power system remain in synchronism or in step with each other. Conversely, we can say instability is nothing but a condition denoting the loss of synchronism or falling out of a step of a synchronous machines. Now let's have a discussion about a definition of power system stability. Power system stability is the ability of an electric power system for a given initial operating condition to regain the state of operating equilibrium after being subjected to a physical disturbance, with most system variables bounded so that practically the entire system remains intact. The other definition of power system stability is the property of the system under normal operating condition to remain in the state of operating equilibrium and to regain its original state of equilibrium even after a disturbance is called as power system stability. Or simply we can define a power system stability as the stability of an interconnected power system is its ability to return to the normal or the stable operation after having been subjected to some form of disturbances. Now, what are the reasons for aggravating the stability problem? Present day, the trend is to transmit more and more power over long transmission lines for economical reasons. Second one, increased generator and the line reactance. Third is interconnection of the power system. Fourth is advancement and the complexities in the modern power system, as it includes hundreds of generating stations and thousands of load centers which are interconnected with each other. Then continuous transient and dynamic disturbances. What are the adverse effects of instability? Now, whenever any one machine falls out of a state with others in the system, it no longer serves its function. A generator no longer constitutes a reliable source of electrical power, and a motor no longer delivers any kind of mechanical power at a proper speed. A condenser no longer maintains a proper voltage at its terminals. Now, whenever the large synchronous machine falls out of the state, it has a disturbing effect on the voltage and it fluctuates between the wide limits, which is highly injurious to the other type of equipment as well as to the human operators, because most of the equipments are designed to operate at a constant voltage level. Instability has a bad effect on service to the consumer load. So these are the adverse effects of instability. If a group of a machine falls out of the state, they are to be disconnected and need to be resynchronized. The out of step detection relay separate the system such that each separated part of the power system will have adequate generation. But sometimes the ordinary fast acting relay trip under out of step conditions also, and therefore tripping some of the unfaulted lines and causing an unnecessary interruption in the services. Now, what are the types of power system stability? Now, first of all, first type is a steady state stability. What is steady state stability? It is the ability of the system to remain stable under the condition of gradual or relatively slow and small disturbances like normal load fluctuation. The steady state stability study is basically concerned with the determination of upper limit of the machine's loading before losing the synchronism, provided that the load is increased continuously or gradually. The steady state stability limit is the maximum power that can be transferred without the system becoming unstable when the load is increasing gradually under the steady state condition. So this is what is the steady state stability. So simply how we can define this steady state stability? That is ability of the system to remain stable under the conditions of gradual or relatively slow and small disturbances like variation in the load, normal load fluctuations, changes in the turbine speed, etc. Second one is a dynamic stability. Now the dynamic stability study is concerned with the small disturbances. So again, if you see the disturbances which was there in case of steady state stability was also small. Here is also the disturbance is small along with the effect of automatic control system such as AVR, that is automatic voltage regulator, and speed governing system. Now the small disturbances continuously occurring in the power system such as variation in the load, changes in the turbine speed, load fluctuation, etc. These disturbances are small enough not to cause the system to lose the synchronism, but they do excite the system into a state of natural oscillations. In a dynamically unstable system, the amplitude of the oscillation is large and they persist for a longer time. The system is said to be dynamically stable if the oscillations don't acquire more than a certain amplitude and die out quickly, that is, the system is well tapped. When synchronous machines are operated with a fast acting voltage regulators, the stability limit of the system is higher than that of the slow acting voltage regulators. So dynamic stability is also concerned with the slow changes in the load as in case of steady state stability. But the main difference between the dynamic stability and the steady state stability is that dynamic stability is achieved by fast acting regulators, whereas steady state stability we can assume slow acting voltage regulators. Now, whenever sufficient time has elapsed after a disturbance, the governors of the prime mover will react to increase or decrease the energy input to re-establish the balance between energy input and existing electrical load. So dynamic stability may occur at a time up to 30 seconds that depends on the inertia of the system and the characteristic of the governor. In a dynamically stable system, the oscillations will be damped out, and after the first few swings, the system settles down to an equilibrium condition with mechanical power input which is equal to electrical power equilibrium condition. Dynamic stability of the system hence is its ability to remain in a synchronism after the initial swing, that is transient stability period, until the system has settled down to a new steady state equilibrium condition. Third type of the stability is a transient stability. Transient stability study is a concern with sudden, large, severe and unrepeated disturbances resulting into a heavy shock to the system. Now the sudden disturbance includes short circuit, sudden removal of the large load on the generating unit and disconnection of the part of the power network. Sudden and large disturbances in the power system causes the acceleration of the machine rotors. The rotor angular differences and the power transfer undergo fast changes. The angular differences may be so large that the machine fall out of the step. So this type of instability is called as transient instability. But if after the sudden disturbance, the system is capable of maintaining synchronism between various machines and returning back to the initial state or closer to the initial state of the equilibrium, then it is said to have a transient stability. Transient stability period is very small. Please remember, this is very important, and it generally takes of the order of 1 second. Now the maximum power that can be transferred without loss of stability when the sudden disturbance occurs, it is called as transient stability limit. The transient stability limits of the system may be different and it may be depend upon following points. Fault clearing time of the circuit breaker. So if the circuit breaker will operate quickly, lesser the fault clearing time, then the acceleration of the rotor will be lesser and it will achieve the transient stability quickly. Then type and the location of the fault, whether that fault is at midpoint of the line, near to the generator bus, near to the infinite bus. So the position will matter to the transient stability. Whether the circuit breaker has a recloser facility or not, it also affects the transient stability. Time of the recloser after fault clearance, 3-pole or a single pole tripping of the circuit breaker. 3-pole and single pole tripping of the circuit breaker topic is going to cover in the topic of methods of improving transient stability and how much power transfer exists before the occurrence of the severe disturbance. So these are the points related to transient stability. Thank you for watching this video. If you have any doubt, please feel free to ask. You can comment on the video. Once again, thank you for watching this video.